Hi everyone. So in this video, we'd like to kind of make a kind of a visual tour of Copper. Copper has been like in heavy development for the past few months, and probably that's going to be good to have like one single video where I just showcase a little bit Copper, what are the new features, new UIs, and so on. But also for people that are not familiar with Copper, kind of go through, for example, at the beginning, I'll go through the concept of what makes Copper Copper, like compared to other like frameworks like ROS. So let's start, right? I'll start with like the concept of Copper and with, for example, this little like simulator we have, right? So this simulator is called like BalanceBot. That's a way for us to show you the Copper without explaining to you what the robot is, right? That's a simple self-balancing rod. So easy to understand, like what are the inputs, what are the outputs, and how it interacts with the world. Okay. So when you start a Copper application, like when it's complete like this, you have a monitor that's called ConsoleMon that helps you to kind of see what's the state of your robot in real time. So you have like a little system information thing. So that's, for example, if you do a screen capture for us to see what you have as a machine and so on, if you have a bug and so on. You have another pane, like when you press 2, you can see basically what is happening in that robot. And a little bit like ROS, Copper applications are based on tasks, right? Like on modules that are communicating from one to another. And you see that's a very simplified view. We'll see that we can expect that a little bit better, but that's just a real-time view where you can basically give to the user a little bit of feedback. Like for example, here you see the inputs, right? You see the inputs on the system on the two encoders. You see also the results of the tasks. Those tasks are like have a different symbol. You see like this is a pure task, like with a little gear. That's a source. And so a source is going to be, for example, a sensor like this one. And if you go to the right-hand side, so it reads from left to right. On the right-hand side, that's going to be the output. You see the applied force that's going to be Newton or the torque, sorry, on the rod. You can also make you can also have the state of errors, right? For example, on this robot, that is a real robot. I have that there, right, with like physically. You don't want that thing to be active when, for example, the rod is completely down. So if you really push it outside of its safety margin, it goes in safety mode, and you see everything turn red, and you have basically here, for example, the balance PID says, "Oh yeah, you're cut off because you're not. It's not safe, right?" Still, the inputs are okay, right? The rail post is okay also because that's not gonna impact anything. But the balancing PID is gonna go into safety, and you can reset the simulator, right, with R, and you can see that it's coming back to life. So yeah, that's in a nutshell what how you look at a Copper application. Now let's go through the other screens. So after the DAG is like this set of tasks. You can look at the latencies, and that's a lot of statistics for you to look at live what could have caused a spike in latency. That's why on the bottom you see like reset latency, because for example, let's say you have something that suddenly adds some jitter that you can actually see there, right? Like if you have like a bump in jitters, you'll see, or the max there, right? You'll see that something is wrong, right? And when you reset the latency, it all goes to 0. And then for example, if you want to manipulate your robot and so on, you can see if whatever conditions actually impacted the behavior or the real-timeness of your robot. You see that with Copper, those timings are absolutely excellent, right? We are measuring in nanoseconds or microseconds, right? That's not even the same unit as what you would see with ROS, and that's for a good reason. Recently, we added this one, the next tab, which is the bandwidth. So the bandwidth gives you, again, in real time, what's the output of your robot in bandwidth, meaning memory and disk. So latency is all about real-timeness. So basically how fast Copper can go from input to output. But bandwidth is going to be how much it can actually push through the system. So here it's kind of bounded by the simulator that is actually at 60 Hertz. So that's why you have like this kind of like 63, 64 Hertz kind of observe rate. But you know what? That's a very good information, right? You see that, oh, something is actually pegging the kind of hertz the Copper can go through. I tell you, Copper, even on a microcontroller, can go to kilohertz, right? So that is really, that's a sign that, yeah, it's not going like full speed completely, right? But that's because we are running in a virtual environment that has actually, that has a loop at that rate. You can see that here, like for example, the Copper list size. So that's the size of how much data your Copper is producing at every single hertz you're seeing. So 64 times per second, it produces 472 bytes of logging. Those are coming from that. Basically, in between all those tasks, we can log the output. You don't have to. You can actually say that you don't want to log them. But by default, it logs everything. So basically, in your log, you'll have a way to actually replay those all this data. The next one, the pools, we will see that a little bit later. That's about for example, like if you have a GPU and memory pools, and keyframes is like to actually save the entire state of your robot. It's not activated on that demo. And you see at the bottom how much bandwidth just the execution of the Copper list is actually pushing through your system. Here it's like ridiculous, but you can imagine if you have images or like heavier data structures, you can try to see if here your robot is not actually hitting the limit of your computer, right? So check out like the channel bandwidth, for example, and if it starts to be in the same ballpark, yeah, you see that you can actually hit like a kind of a bandwidth limit of your system. A very cool way to actually see that in real time, and you can check what is happening. Here it's very stable, right? Because this robot is very predictable. Now, on the disk side, when we get those Copper lists, we serialize them straight as they are. They are like a block of memory that we serialize, and out of that serialization, we can actually optimize them. For example, if you have only zeros in there, it will actually, instead of encoding like 64 bits of zeros, it might actually encode only 8 bits. So that's where you see the CL efficiency. So you see here that, yeah, we are at 60%, meaning that basically, yeah, we log 300 bytes per Copper list instead of 472. That's interesting for you. For example, if you realize that your tasks are sending a lot of zeros from one to another, like a kind of, I don't know, skinny matrices or whatever, right? Or like on the opposite side, if you have a lot of like arrays that needs to be actually copied over, you see that efficiency is going lower. And that gives you a hint about like, yeah, what's going to be the relationship between your bandwidth on the execution side and on the serialization side. And you see actually the bandwidth we touch on the disk, which is like 20K per second. That's absolutely ridiculous. So those are the pools. We can explain that later. And you can see on the last tab, we have like structure logging with Copper. It means that we have a way to log only data out of your traces, right? Those debug logs are like really kind of text log, but when you use them with Copper, you don't actually log text. You log only a reference to the message and what is the content of the parameters to rebuild those messages, right? So it's super optimized, so you can feel free to actually add those debug exclamation point in your code base, and that won't actually slow down your robot. All right, so we saw like that was a kind of a tour of the real-time part of your robot, right? You can imagine you would see that screen when you are SSH to your robot and when you want to run it, right? Instead of a simulation, right? It's easier for me to show you there, right? And that gives you like the real-time part of it. But when you, so let's kind of like roll back a little bit. And when you are designing your robot, sometimes you want to see, okay, what are the what is the shape of your robot? Basically, what is connected to what? Let's say you have a new I don't know, a new person on board, and you want to show them, okay, that's basically the architecture of your robot. We made a tool for that called JustDag, and you can see in there that that's basically the same thing as what you saw in the real-time environment. But you can see that now we really have, like, it's clear what is the types. You have one out that is actually the type of the out. That's Rust type. Here also you have another one, and you can see also that we have configuration, right? Like we have a bits of configuration. Sometimes, for example, here that runs on a Raspberry Pi, a standard Linux machine, but we want to put this encoder on like specific pins. So we have a config that you can put in the copper config.run. So you see, okay, you see what's the payload between the two, and you see also here that like two inputs are arriving to these tasks that are taking two inputs to one output. So you can imagine that the scheduler of Copper will basically schedule this one, then this one. Once it has an input, it will schedule this one, so it can get the output of that. And then you are here, like you arrive into your actuator. That's just one motor, right? That's the chip that is basically driving it. We have a Raspberry Pi driver for it, and also we have like some config associated to this, and we have like a legend there if you don't know what it is. So blue for the sync, and green for the sources, and orange for the task, for example. All right. Now, so you see, so this tag was, you don't even need to actually run your robot, and you can actually, it is generated straight from that file, the main config file of your robot. Let me show you. Oh, let me show you with Vim, a little bit better. And you recognize, right, those parameters and so on. So all those tasks, they are basically defined with an ID, a type of the task itself, its config there, right? And at the bottom, you'll see that we connect them, right? We connect a source, destination, and what type of payload you want to actually send from one to the other. It's very similar to those like channels in ROS, except that it's a little bit more static, right? Like everything is actually taken from that config file, and that's going to compile your robot in one big executable. Here we are pluggable in terms of monitoring. So the ConsoleMon, that's the one you saw with all those screens on the top, and you can configure it here. So yeah, so this JustDag, right, was taking the static part of your robot. But now we have a new feature that actually can combine what you've seen in the logs, what the robot have seen and logged, right, in terms of performance, to this DAG. So it's called DAG stats here. Like you can see in the just file what's the command. It's the same way you generate it, and suddenly you have exactly the same DAG, but suddenly you see like new things. For example, you have a log table there, right? Log performance, right? So you see, okay, what was the latency and so on, but that's from a log, right? The log that has been saved here in that directory. You have like the balance, this one, right? Exactly this one. And you recognize exactly the same one, except you have like little circles, and you can see basically also the rate pair message there, right? So it's pretty useful when you have a series of logs, you want to, I don't know, compare the performance out of it. That's a way to actually visually do that, like very quickly. You can see, okay, number of samples, number of data that got missed, and so on. That's pretty cool, right? Now, okay, talking about logs, in those logs, they are like copper files, not copper. Those are like, this is a private format for copper for logging things, right? So don't worry, right? So we make no guarantee about what's going to be the format of this logger, but we have an API that is able to read that log, and you can export it. So you can export it to, I don't know, CSV, JSON, but one of the cool ones is basically MCAP. So if you do just MCAP, you will see that okay, it compiles it with like the current like version of the code base, because like I said, it's an API, so it needs to basically recompile your messages and so on. Once you work on your robot, that's gonna do like only like a differential compilation. Right? That's only a one-shot thing. So here it compiles the balance-bot-log reader. So that's going to be the executable that transformed this private format for copper to the correct format. So here you see a little bit like screen where you see where it exports the logs in an MCAP format, the standard one. So it gives you like the number of messages, channel, and schema, and you can see like some statistics about like how many messages it got logged from all those like channels. And also what's the schema, right? Like, so it will redescribe for the MCAP format and infer what was the schema between those like Rust messages. And the cool thing, like when you go to Foxglove, here you can basically open the source file. So that's in the example balance bot logs. You have this balance.mcap. And here you go, you see, like for example, you see when it failed, right? You see like the angle that was at 360, right? And you have like here like the power it actually applied to the rod. So yeah, you have a way to basically export to Foxglove directly your results and visualize them. The support is like kind of like a minimum right now, right? But we will add like new features, new types as they arise, right? Like and that's cool to see, like you see the schema that worked well with like all the start and end time of processing and the status text, the thing you saw in the interface is there too, so you can actually correlate this data into your Foxglove visualizer. Right. So now something cool. We often talk about like determinism with copper, right? And let me show you how it manifests, right? Like what does it mean and why it's important. So when you're running a robot, you often have like a source of non-deterministic execution. Basically, like you have like asynchronous data that is coming from all over your robot and concurrently. So when you try to get to basically record a log out of your robot and then try to resimulate or replay this log, you might have actually a different behavior depending on how your runtime will actually reschedule and re-execute your robot. But copper is deterministic. So let me show you. Let's run for a while, like this example robot, right? It's just like a bunch of like noise coming in like through like a bunch of tasks. It goes pretty quick, so we need to it goes like a 500 kilohertz. So okay, I think we have enough. So that creates logs. So if you look at that, you will have like a lot of logs. We have gigabytes of logs because this robot is really fast. And what you can do is to take back those logs, re-inject that into your own code that you can debug. For example, you can put like a breakpoint on your code base and replay exactly what happened during those logs. And what you can do is you can produce logs out of those logs. And that's what like this just resim command, you can look at the just file, right? It's just like another executable, right? That's what this thing does. Basically, it takes those logs, replay exactly your robot, and will produce out of it like output logs. So you see that it's again like it's going like super fast, but it's getting like that time instead of like being like kind of random, it takes the inputs from those input files, strip the output, and recreate the same log basically. And we will check that. So we will need to wait as long as we did the first time around. Going through this. I hope I have enough this space because that is going really fast. The bandwidth and the latency are completely insane. So now we have those pieces of logs, right? Let's take the first one, right? They are actually they are sequential. They are basically what we call slabs. We don't want to have like a too big of one file, and we pre-allocate them so we are sure that we have space, and we continue like that. So let's do like the compare command that's gonna like binarily compare what happened the first time, where the robot was actually the robot itself, with the second time where we took the inputs. We took the inputs and we replayed and we put the output as we were logging. So it's just another execution with the same input. And you see, it's completely identical. If they were like different, you would have like an error. Right? I put like two different files, you have an error. So yeah, you see what it means now, like determinism. It's every time you re-execute and replay one log, you always have the same result. So you can basically be sure that even if you store those logs on like a let's say a collection of like snippets you want to replay because you want to have, I don't know, those corner cases for your robot, like iron out, right? When they are green, they will be always green with the same code, of course, right? And when they are red, they will be always red with the same code. And that allows you to have like a strong non-regression library of cut logs, so you are sure you're not regressing while you are actually developing your robot. That's a very important feature of Copper. So here is another demo of Copper, but this time with some machine learning and inference in the loop. So what we do here is basically we stream that camera that is actually taking the image from the driver, the camera driver from Copper, and we do like a simple like human pose from HuggingFace using YOLO V8. So yeah, here I print out the debug. It goes really quickly. You see, like already it was 60,000 like cycles. The rate is like 15 hertz because it's in debug, right? And you see that mostly all the time is taken by YOLO, and we only have like a very few microseconds of overhead over this. So let's see how it looks like in the inside, right? So if you look at the DAG, it's very simple. You get the camera driver that is already in the driver called QGStreamer. This is like a standard one that given with Copper. We have a little translation task that takes that GStreamer buffer. The GStreamer buffer is really like a temporary one that only GStreamer own, right? So I need to copy that to actually a buffer that can be used for the inference. We stream this buffer to Rerun on that visualization tasks. And the other one, the same buffer, we route it to this YOLO task that will just take the input, right, on that format. And as output, it will get poses and then feed that also to that visualization that will make that basically the synchronization between the two and display on top of the image in Rerun those poses. So I won't go into like the code itself, but you already have like a good framework for you to actually use any type of ML algorithm in the middle, right? That's the way you can do that, and you can do that also with like I don't know, like LiDAR points and so on. So that's a good starting point for you to actually show not only how to use some ML from Rust, but also to use the visualization from Rerun that is pretty amazing. Like you've seen that everything was working, and that's like a pure Rust API. So check out that example. It's called like human pose in the example directory. Next up is embedded development. That's also something that has been implemented recently. Like originally, Copper was only be able to run on like a standard computer, a standard OS, right? Like everything we saw so far is actually on Linux. But now we are able to target microcontrollers, and you'll see in the wiki we have a list of components that are marked like either like bare metal or no STD. It means that they are targeted towards microcontrollers more than actual like OS based. Some of them are both. So you can see, for example, the serial ports based stuff can be used with both standard Linux or Windows or macOS and embedded. So you have like a ELRS, for example, like the thing we use to decode the radio commands things. Those are both actually available on platforms. So that example will also show you a new concept that we recently added. Actually, couple ones. One is you see that there are now missions. You see here like that's a default basically configuration of your DAG, and depending on like let's say a big change. For example, here we have the standard like flight controller without like a flow sensor, and here we have one with a flow sensor, and that's a good way to demonstrate. So you'll see that right in the copper config.run how we actually put components and links attached to one mission or the other. So you can have like some flexibility to basically compose your DAG depending on what you want your robot to do. It could be like an hardware difference like this, like there is like a sensor that does exist in one configuration or the other, like basically two different robots. But you can have also different, like that's why we call missions, different like goals. For example, you could have a robot that is only deployed to capture data. So you could have a mission that is data collect, and the other one is basically production. Like basically, your robot is doing their normal behavior. So that allows you to like really reuse a bunch of things between your missions. For example, data collect use the same type of sensors usually than the production mission. So you can reuse them from one mission to the other, and you see that there, right? Like for example, there is only one part of the tree that of the DAG that changes. So that's one thing. And another thing that is new, so you see that it's like way more complex here, right? Like in terms of robot, that's more like a realistic one where you have like a bunch of sensors, you have IMU, AHRS, and so on, right? Like so, it's a bit more complex. It goes always like from left-hand side all the sensors. You see, for example, the IMU there, the command, the radio commands there, right? To actuation on the right hand side. Those are basically motors of your flying machine here. Like that's a quadcopter. That's why there are 4 mixers for the 4 motors. And what is new, and we can show that there actually. Those are bundles of resources. So we realize like pretty quickly that when you have like let's say a flight controller like this, right? You need like resources that are on like the board. It could be the board, or could be like your OS, like threads, or like serial ports, or and so on, right? And that's the thing that is kind of challenging, because you can imagine that I don't know, MSP could be on one serial port, the RC could be on another, right? So you need a way to say to Copper, you know what, you have resources available for that platform, but I want that component to be able to use that resource. It's like a hardware abstraction layer, or HAL. And that's what you see there. You see that, oh, you know what, for example, this cable select for the gyroscope is used by the AMU. Or this green LED on the board, right? There is a green LED, like a GPIO, that is wired in the flight controller. Oh, that's on the ACT LED. So I don't know where it is. Yeah, this one, for example, right? That's a little bit feedback I give to the user when they use the thing. So that's a way to really map the resources of your hardware towards your tasks. So your tasks are kind of like very generic. So the MSP tasks, for example, are just taking serial ports, and they don't care where they are coming from. That's a good way to really split the logic between the hardware and the way you are actually running it on the DAG itself. So yeah, so this flight controller example, you can refer that, like if you want like to reuse like bundles that we also give with Copper, and kind of give yourself a little bit of flexibility for your robot deployments, depending on what hardware you use in what environment. So next up in our tour is how you probably realize that Copper is like monoprocess. So basically, by default, unlike ROS, it just bundles your tasks together in one process. And this is by choice, right? Because most of the time, you don't need a distributed system. You have one robot doing one thing, and when you want to distribute your processes, usually it means that either you are communicating to another system, or you want safety, redundancy on your own system, on the same robot, but then it's very precise. It's going to be like, okay, mode A, mode B, mode A is running, mode B is kind of like dormant, and when you want to switch off, you have a kind of like a keep alive between the two, and mode B like takes over if mode A crashes and so on, right? For isolation. And that's completely possible with Copper. That's what I will show you here. How do you make a Copper talk to another Copper, or any other system that supports this data, right? So I show that with Copper, but we can do that also from Copper to ROS2. But here it's going to be Copper to Copper. I'll show you like a little bit like the fastest way to actually distribute your Copper system. So let's look at what we are about to do. So that's so one way of talking to another process with Copper is using the Zenoh bridge. The Zenoh is a protocol that has been developed in Rust that is pretty fast and like can use like shared memory, and can do like a swarming, like basically having like one robot forwarding a message to another one in a distributed fashion. So very, very cool for like a real world deployment. So in that demo, we just have like a message, like that's a pure standard Copper message called ping here. We send that to a bunch of inputs on the Zenoh bridge, and as outputs, we have we log basically the responses from the other side. So imagine that bridge is basically a bridge to another system. So inputs are plugged to the outputs of the other system, and those outputs are plugged to the inputs. So here we basically send messages and receive messages and log them. Okay, so that's one side, that's the ping side. of that demo. And if you look at the Pong side, you can imagine what the Pong is doing. Basically, you have the same bridge as what we used before, but as outputs, it will go in your tasks and will respond to those channels on the Zenoh bridge. And you see the wire format, it's being coded there by default, but we can set a format per channel. And that's what we are doing here. Like, for example, this first message is in bin code, the second one is in JSON, and the third one is in CBOR. But look, we are using exactly the same message as an input on the Copper side. So you see the flexibility of that bridge, right? You can basically set any number of channels in any number of formats as long as it is supported by the serialization from Rust, and then you can communicate with another system on the other side. So very, very flexible system that I can demonstrate there. So let's say we can use the ping. You can start the ping side, and we can start the Pong side. And you see, yeah, on every single pings that side is sending, this side responds, send it back, and you see them like those ping numbers that are logged from all those like channels in different formats. Very, very easy to do or to implement, and and very flexible to deploy on the field. Thank you all for watching, and I hope you enjoy this tour of Copper. And feel free to join us on our Discord server. You have the link on the top of our README or on our website. And also stay tuned on that channel on YouTube, where we will post like showcases from our community or talks and so on, like we have been doing for the past few months. Thank you so much.